on how to transform time functions to complex frequency function using Laplace transform. For our next problem, we have the Laplace of the step function, which is represented by u of t, is equal to 1 over s, based on our Laplace transform table. So we will prove this, So by turning it into a complex frequency function, we need to get the improper integral from 0 to infinity of e raised to negative st times 1 times dt. The one here also represents the step function. So for simplicity, we will reduce it to improper integral from 0 to infinity of e raised to negative st. And by basic integration of exponential functions, we could substitute this in this formula. So we will just substitute this term into this formula. So negative 1 over s e raised to negative st dt from our limits 0 to positive infinity. So let's evaluate. What happens if we substitute t to positive infinity? We will have a very large number. Basically, we cannot plug in positive infinity as it is a set of a very infinite number. So we could just plug in a very large number. Let's say s times capital A. So capital A represents a very large number. So what happens if we substitute a very large number or e raised to negative value of a very large number? So it will just yield to 0. So this term will just be 0. And minus the second term. Let's analyze. So negative 1 over s e raised to negative s times 0, it will then result to positive 1 over s e raised to negative 1 times s times 0 is 0. And that yields to 1 over s times 1 because e raised to 0 is 1. So it will just simply be 1 over s. Thus proving our Laplace transform. Next frequency function using Laplace transform. In this case, we will get the Laplace transform of t times u of t, which is equivalent to 1 over s squared based on our Laplace transform table. So we will prove that. So getting Laplace transform of t times u of t would be equal to the improper integral from 0 to positive infinity e raised to negative st times t times u of t times dt. So u of t will just be equal to 1. So simplifying, we'll get improper integral from 0 to infinity of e raised to negative st times t dt. By observation, we could see that this is solvable by using integration by parts. So the formula for integration by parts is uv minus integral of vv. So we will now assign values for u and vv. So u would be equal to t, and the derivative of t will just be dt. Then the value for dv is e raised to negative st. And if we integrate this, we will get negative 1 over s e raised to negative st. So we will plug in these values in this equation. So e negative 1 over s e raised to negative st times du, which is dt. So we will bring out the constant. So t times 1 over s e raised to negative st minus, this will be a plus sign because we will bring out the negative sign. So 1 over s times integral of e raised to negative st dt. From our previous problem, we have proved that the integral of e raised to negative st would be 1 over s e raised to negative st. So let us copy this term. Raised to negative st. All this limit from 0 to positive infinity. Before we evaluate this term, we will just bring out the common terms, which is e raised to negative st. E raised to negative st times t, or negative e over s, minus 1 over s squared. All of this from 0 to infinity. If we evaluate the term, or if we plug in positive infinity e raised to s raised to infinity times negative infinity over s. Oh, sorry, this will not be negative. It's positive. Minus 1 over s squared minus e raised to negative s times 0 times 0 over s minus 1 over st, s squared, sorry. So this term will just be equal to 0 because e raised to negative s times a very large number will yield to 0. So this will be 0 minus, evaluating this term, e raised to negative s times 0 will be e raised to 0 times 0 over s will be 0 minus 1 over s squared will be negative 1 over s squared. E raised to negative, or e raised to 0 would be 1, so minus 1 times, or minus, or times 1 over s squared will just yield to 1 over s squared. Now let's continue on transforming basic time functions into s domain. So for our next problem, we have the class of e raised to n times u of t is equal to n factorial over s raised to n plus 1. So we will prove this expression. So the Laplace of t raised to n times u of t is equal to the integral from 0 to infinity of t raised to n times u of t times e raised to negative st times dt. We could simplify this because u of t is also equal to 1. So we will come up with the improper integral from 0 to infinity of t raised to n e raised to negative st dt. So from observation, we could say that it is solvable by integration of parts. So writing down the formula, we have uv minus integral of v du. Let's assign now values for this equation. U would be t raised to n, du would be n times t raised to n minus 1 dt. And for our dv, we will have e raised to negative st times dt. And by integrating this, we will come up with negative 1 over s e raised to negative st. So by knowing these values, we will now plug it in this formula. So equals to uv, which is t raised to n times minus 1 over s times e raised to negative st minus the integral from 0 to infinity of v, which is 1 over s, negative 1 over s, e raised to negative st du of n times n raised to n minus 1 dt. Let us not forget the limits in this outer part. So we can now evaluate this part before we proceed in this integration. So plugging in into the values of t, we will have infinity raised to n times negative 1 over s e raised to negative s times infinity minus 0 raised to n negative 1 over s e raised to negative s times 0 minus this term 1 over s e raised to negative st n times t raised to n minus 1 dt. So by evaluation, we could say that this first term will just come up with 0 because infinity raised to n will just be 0 and e raised to negative s times infinity, which would be replaced by a very large number, would be also equal to 0. Minus this term, so we could say that 0 raised to n will also come up to 0. So 0 minus 0. Minus this part, we will now be simplifying this so we could direct to integration. So minus, let's bring out the coefficients or the constants. So plus, since there's a minus sign here, n over s times integral from 0 to infinity of e raised to negative st times e raised to n minus 1 dt. I want you to observe this form with our original formula. So let us simplify this. So the integral from 0 to infinity of our original integration, e raised to n e raised to negative st dt is equal to this part. Since it is an equation, it is equality, so it must be equal. So n over s times integral from 0 to infinity of e raised to negative s times t raised to n minus 1 dt. As we could observe, this expression is also the same with this expression, but their exponent in the t term is has a minus 1. So we could assume that it is recurring. So to prove that it is recurring, we will substitute values for n so that we would come up with a recursion formula. So let us try to simplify this by the Laplace, or concluding that the Laplace of t raised to n is equal to n over s times the Laplace of t raised to n minus 1. So let's now Laplace of t raised to 1 minus 1. So we could say that the Laplace of t raised to 1 minus 1 would come up to be Laplace of t raised to 0, or we could replace that as 1. And from our previous derivation, the Laplace of 1 is 1 over s. So 1 over s times 1 over s would come up to 1 over s squared. So the Laplace of t raised to 1 is 1 over s squared. Let's write it here. Now let's prove the Laplace of t squared. The Laplace of t squared would be 2 raised to s times the Laplace of t raised to 2 minus 1. So 2s would be, 2s times Laplace of t, 2 minus 1 would be Laplace of 1. Our Laplace of 1 here is 2s, or our Laplace of 1 is 1 over s squared. So we will substitute it with 1 over s squared. And we will come up with Laplace of t raised to 2 over s cubed. So let's write it here. 2 over s. And next would be if n is equal to 3. So Laplace of t raised to 3 would be 3 raised to s times the Laplace of t raised to 3 minus 1. So 3 over s times Laplace of t squared. So Laplace of t squared is 2 over s cubed. So 3 over s over 2 over s cubed. So Laplace of t raised to 3 would be 6 over s to the 4th. And I'm gonna stop here because it will be just the same. So when you follow this formula, we will come up with these values. So as you can see, as we increase the value of n, our value on our numerator is increasing by n factorial, and on our denominator, as we increase the values of n, we will be increasing by s raised to n plus 1. So we now prove that the Laplace of t raised to n u of t, continuing with transforming time domain to s domain, we will now have the problem. The Laplace of e raised to at times u of t is equal to 1 over s minus a. So we will prove this expression. So in our previous Laplace transform, we will get the integration from 0 to infinity of e raised to negative st times our f of t, which is e raised to at dt. We will be putting u of t as 1, so we will disregard that. So we can simplify this expression as integral from 0 to infinity of e raised to negative s plus a t dt. So we can simplify this in this format. So now we will use our basic knowledge of integration. raised to minus s plus a minus s plus a times t with our limits from 0 to infinity. Let's now plug in our limits. 1 over s plus a minus s plus a rather times e raised to negative s plus a times infinity minus e raised to negative s plus a times 0. We now evaluate this expression. E raised to a large number would be 0 minus e raised to a number times 0 would be e raised to 0 minus e raised to 0 times 1 over negative s plus a. So we will now come up that e raised to 0 would be 1. So it has a negative sign, so it must be negative 1. So negative 1 times 1 over negative s plus a would just be 1 over a, would just be 1 over negative s plus a. It will now be simplified. When we distribute the negative sign, we'll only have s minus a, thus proving our expression of our Laplace transform. Now let's continue on transforming time functions into complex frequency function. Today, our notation for the Laplace transform is t raised to n times e raised to at is equal to n factorial over s minus a raised to n plus 1. So we will prove this expression. So in performing Laplace transform, we need to put this in this kind of integration. So the Laplace transform of t raised to n times e raised to at is equal to the improper integral from 0 to infinity of t raised to n times e raised to quantity a minus s times t dt. So as you can see, we have already simplified the e raised to at and the e raised to negative st so that we could already move on to this equation. So by observation, we could conclude that we could solve this by integration by parts. So this is the formula for integration by parts. Integral of u dv is equal to uv minus integral of v du. So we need to assign values for these variables. So our u here in this expression would be t raised to n. Our du would be n times t raised to n minus 1 times dt. Our dv now will be e raised to a minus t times t dt. While our v here is 1 over a minus s times e raised to a minus s times t. So by plugging in the values in this formula, we have plugged in, and this is the result. So t raised to n times e raised to a minus s times t over a minus s from 0 to infinity. So this is the term uv minus the term of integral of v du. Our v here is this term, which is 1 over a minus s e raised to a minus s times t times our du, which is n times t raised to n minus 1 dt. So we could now evaluate the outer part, which is the uv term. So if we substitute infinity onto the t raised to n, and we could also substitute it in the expression, in the exponent in the e term, we could cancel it, or we could simplify it as 0, because e raised to a negative infinite number is equal to 0, minus the term on the 0 limit, e raised to
e raised to 0 would be 1, but 0 raised to n would be 0. So it will also be 0. Now, let's evaluate this part. So we will now move out, or we will put it on the outside part of the integral, all the constants or all the coefficients. So we will be having n over a minus s times integral of t raised to n minus 1 e raised to a minus s times t dt. So as you can see, this part of the integration, or this term, is also equal to this Laplace, or this original Laplace integration. So we could assume that this term is also recurring. So to prove that this is a recurring function, we should we should simplify it and assign values for n in order for us to conclude the recursion formula. So our proposed formula is the Laplace of t raised to n times e raised to a times t is equal to n over s minus a times the Laplace of e raised to at times t raised to n minus 1. So if n is equal to 1, we will be having 1 over s minus a squared. If n is equal to 2, we will be having 2 times 1 over s minus a cubed. And if n is equal to 3, we will be having 3 times 2 times 1 over s minus a raised to 4. So by observation, we could conclude that as we increase the value of n, we will be also increasing the value of the exponent in the denominator side. While as we increase the n, we would be having an n factorial in the numerator side. Now, that's why this is our conclusion. The Laplace of t raised to n times e raised to at is equal to n factorial over. Now let's continue on our expression. Laplace of cosine b times t times u of t is equal to s over b squared plus s squared. So in order to perform again the Laplace transform, we need to perform this integration. So the improper integral from 0 to positive infinity of e raised to negative s times t times cosine bt times dt. So we need to perform also the integration by parts. So the integration by parts, as we recall, has this formula, uv minus integral of v du. So our u here is sine dt, our du is d cosine vt times dt. Our dv here is e raised to negative s times t, while our v is negative 1 over s times e raised to negative st. So simplifying this formula and plugging it our values, we will get into this expression. 1 over s minus b over s times negative sine bt over s times e raised to negative sine st plus b over s times integral from 0 to infinity of e raised to negative st times cosine bt dt. So we will distribute the outer coefficient which is b over s. So we will get 1 over s plus b sine bt over s squared. Since we have distribute the s squared, the s in the denominator, we will get the s squared times e raised to negative st from 0 to infinity minus b squared over s squared, since we also have b over s in the coefficient in the integral part. So we will have b squared over s squared times integral from 0 to infinity of e raised to negative st cosine bt dt. So as you can see by observation, as we continue to integrate this expression, we will be having a continuous integration. So in order for us to terminate this expression, we need to assign variables in order for us to equate each one of them. So we will equate it in the original integration, which is e raised to negative st cosine bt dt. So we will let this as y. So we will have this linear expression of y y is equal to 1 over s plus b times sine bt over s squared e raised to negative st from limit 0 to infinity minus b squared over s squared times y, so that we could now simplify our expression. Now let's evaluate this part of the limit. If we substitute infinite in the value for t, we will be having a zero term, and if we substitute 0 in t, we will also be having 0, since sine of b times 0 will be 0, thus canceling out all the terms, and we will be remaining with a term of 0. So all that is left is this term. So s squared plus b squared over s squared times y is equal to 1 over s plus e raised to negative st times b times sine bt over s from limits 0 to infinity. So if we now evaluate this expression, we will also be having 0 if we substitute it with infinity, since e raised to negative s times infinity would be 0, minus the limit on the 0 term. E raised to negative s times 0 will be 1, but sine b times 0 would be 0. So it will all be just 0. So 0 minus 0 is 0. Thus, we will be left with s squared plus b squared over s times y is equal to s. And then we will simplify this equation. Thus, we will be having s over s squared plus b squared, thus proving our expression here. For our next expression, we will prove the Laplace of sine bt times u of t is equal to b over b squared plus s squared. So in order for us to perform the Laplace transform, we will put this function into this integration. So the improper integral from 0 to positive infinity of e raised to negative st times sine b of t bt times dt. So we will perform integration by parts. Let us assign values for uv minus vdu formula. So u would be sine bt, du would be b cosine bt, dv would be e raised to negative st times dt, and v would be negative s 1 over s e raised to negative st. So plugging it into our formula, we will be having negative e raised to negative st times sine bt all over s with limits 0 to infinity plus b over s times integration of e raised to negative st times cosine bt dt. So evaluating this outer part, if we substitute infinity into the value for t, we will be having 0. Minus, if we substitute this term into 0 with the values for t, we will also be having 0. All that is left is b over s times integral from 0 to infinity of e raised to negative st times cosine bt dt. Now we will repeat the procedure of the integration by parts. So u would then be cosine bt. Our du would be negative b sine bt dt. dv would be e raised to negative st dt, and v would be negative 1 over s e raised to negative st. So substituting it again to the formula of the integration by parts, we will be having b over s times negative e raised to negative st cosine bt over s from limit 0 to infinity minus b over s times integral of sine bt dt from 0 to infinity. So we will first evaluate this term. So if we substitute values for t in infinity, we will be having 0. And if we substitute 0 to the values of t, we will also be having 0. So it will just cancel out. And as you can see, this integration would also be continuous. So in order for us to terminate this expression, we need to equate this in the original expression and assign a variable so that we would be having terminating expression. So we assign y to the integration of sine dt dt. So y is equal to b over s squared minus b squared over s squared times y. Then we simplify this expression and we will come up with this expression, b over b squared plus s squared, thus proving our Laplace transform. Continuing with our Laplace transform, we will now be having the function e raised to negative at times cosine bt, and we will find its equivalent complex frequency domain. So we will put it in the integration of e raised to negative st times e raised to negative a times t cosine bt dt with the limits 0 to infinity. It will then be equal, or it will be simplified as this. Since it has the same base, the exponents will be combined. So the integral from 0 to infinity of e raised to negative s minus a times t cosine bt times dt will then be the integral of e raised to negative quantity s plus a t cosine bt dt. So in this integration, we will also be using integration by parts. So the integration by parts formula is uv minus the integral of v du. So let's assign values for that formula. So u would be cosine bt, du would be negative b sine bt dt, dv would be e raised to negative quantity s plus a t dt, and v would be negative 1 over s plus a e raised to negative quantity s plus a t. So we plug in the values for that formula and we will come up with this equation. Negative cosine bt over s plus a times e raised to negative quantity s plus a times t with the limits 0 to infinity minus b over s plus a, since we already put out the coefficients, times integral of e raised to negative s plus a t sine bt dt with the limits 0 to infinity. Firstly, we will evaluate this part of the equation. So if we plug in infinity to the variable t, cosine b times infinity over s plus a times e raised to negative s plus a times infinity will just be resulting to 0. Minus, if we plug in 0 to the value of t, negative cosine bt over s plus a times e raised to negative s plus a times t would be resulting to negative 1 over s plus a. Minus this part of the integration. Since we will be having integration by parts again, we will perform the preceding formula. So we have u as sine bt, du as b cosine bt, dv as e raised to negative quantity s plus a t dt, and v equals negative 1 over s plus a e raised to negative quantity s plus a t. So we bring out this part of the equation. It will only result to positive 1 over sa. So we bring out that term minus this equation. By performing the integration by parts, we will have minus b over sa times uv, which is negative e raised to negative s plus a t sine bt all over s plus a from limit 0 to infinity, plus b over s plus a times integration of e raised to negative s plus a t cosine bt with limits 0 to infinity. So we can now see that this is a recurring integration, and we need to terminate that equation. So we set y, or we set the Laplace of e raised to negative s a t cosine bt as y, so that we could simplify the equation. letting y as this part of the equation, or this term, we'll come up with this part of the equation. So y is equal to 1 over s plus a minus b over s plus a times 0 plus b over s plus a times y. Since we already evaluated this part of the equation, we only come up with an answer of 0. Since e raised to negative s plus a times infinity would be 0, thus making the whole term 0, minus e raised to negative s plus a times 0 would be 1, but sine b times 0 would be 0, thus making also the term 0. So it will be 0. Plus this term, which is b over s plus a, but remember that this term is our y, so we simplified it as y. Distributing this coefficient, we will be having y is equal to 1 over s plus a minus b squared over quantity s plus a squared times y. So our goal here is to simplify the equation and to find y, which is, remember, our Laplace equation. So equating both sides by positive b squared over s plus a squared y, this term will cancel out, but this term will be will have the equation positive b squared over s plus a squared times y. So we will come up with the simplified terms. So s plus a squared plus b squared over s plus a squared times y is equal to 1 over s plus a. And performing finding the value of y, we will then result to s plus a all over s plus a squared plus b squared. Thus, this is the value of the Laplace of this function. For our last derivation, we will take the Laplace of e raised to negative at times sine bt and transform it into a complex frequency domain. So, by integral from 0 to infinity of e raised to negative st times e raised to negative a times t sine bt dt. And we could simplify this integration since it has both bases. Our exponential rule would be if both bases are multiplied, we could combine their exponents. So we simplified it as the integral of e raised to quantity minus s minus a times t sine bt dt, and it will be equal to the integral of e raised to negative quantity s plus a times sine bt dt. So in this part, we will also be using integration by parts. So having the knowledge of the formula of integration by parts, uv minus the integral of b du, we assigned u as sine bt, du as b cosine bt, dv as e raised to negative s plus a dt, and v is equal to minus 1 over s plus a times e raised to negative s plus a. So, from the formula, we plug in these values. So, we will get negative e raised to negative s plus a times sine bt all over s plus a with the limits from 0 to infinity, minus the integral of negative b cosine bt e raised to negative s plus a all over s plus a dt. So we could evaluate this part of the equation, which is the uv. So if we substitute the value of t with infinity, we will get e raised to negative s plus a times sine b times infinity all over s plus a, we will just get 0. Minus, if we substitute t for 0, sine b times 0 would be 0, thus making all the terms 0. So this will cancel out. We will all be remaining with this term. So we could simplify this term as b over s plus a times the integral of cosine bt times e raised to negative s plus a dt. And we will again perform the integration by parts formula. U would then be cosine bt. du would be negative b sine bt. dv would be e raised to negative s plus at dt. And v would be negative 1 over s plus a e raised to negative s plus a times t. So applying the formula for integration by parts, we will get b over s plus a, because we have a constant on the outside of the integration, times this integration, minus cosine bt times e raised to negative s plus a t all over s plus a, minus negative b over s plus a times the integral from 0 to infinity of sine dt e raised to negative s plus a dt. So, as before, if we have a continuous or if we have a recurring integration, we would be equating both sides by the original equation, which is this one. So, let us assign a variable. So, for this, let's assign y as the integral of sine bt e raised to negative s plus a dt, as the same as the first or the original equation. So, equating both sides, y is equal to b over s plus a times this term. Evaluating this term first, we will get cosine b times infinity raised to, or times e raised to negative s plus a times infinity all over s plus a will just lead to 0. So this term would be 0. And if we substitute t for 0, cosine b times 0 would be 1. E raised to negative s plus a times 0 would be 1 all over s plus a. So it would be 1 over s plus a. But remember, we have a negative sign here. So it must be negative 1 over s plus a. Times this term. We have negative b over s plus a. But we have this term which is equivalent to y. So we will put it as y. So then we have our simplified equation. Y is equal to b over s plus a times this whole term, 1 over s plus a minus b over s plus a times y. So we have simplified this. 0 minus negative 1 over s plus a would just be positive 1 over s plus a minus this term. So we must first distribute this coefficient, and it will lead us to this expression. Y is equal to b over s plus a squared minus b squared over s plus a squared y. And through our knowledge of algebra, we will get the value of y, to get the Laplace transform for this function. So we end up with this term. Y is equal to b over s plus a squared plus b squared. Thus, this is the Laplace of this function.